In the silence of the outer solar system, there is a moon that never raises its voice. It does not glow with storms like Jupiter. It does not sing with rings like Saturn. It simply drifts pale, cracked, and quiet. Yet beneath that frozen stillness lies one of the most extraordinary secrets in the known universe. Europa, a world smaller than our moon, yet holding more water than all the oceans on Earth combined. A world so cold that its surface has frozen into a crust of fractured ice, but so alive underneath that entire continents of ice slowly shift, break, and heal themselves over millions of years. Tonight, we descend into that silence. We will follow the faint gravity tides that knead Europa's interior, trace the invisible heat rising from a metallic core, and listen to the geological heartbeat that keeps an alien ocean warm beneath a frozen shell. Because beneath that shell, in the darkness of 100-kilometer deep ocean, there may be volcanoes erupting underwater. There may be entire landscapes sculpted by superheated minerals. And there may be, for the first time beyond Earth, conditions suitable for life, not fantasy, not fiction, but a possibility grounded in physics, chemistry, and the strange engineering of icy moons shaped by giants. This is the hidden ocean of Europa, a silent world beneath the ice, where the laws of geology never stopped working, and where the story of planetary oceans may be wider, deeper, and older than anything on Earth. Chapter 1: The Birth of Europa. In the beginning, long before Europa became a symbol of mystery and possibility, it existed only as a fragment of chaos, an unnamed shard in a newborn solar system that was still violent, unstable, and incandescent. To understand Europa's hidden ocean today, we must first understand the world it once was. Every ripple beneath its frozen shell, every chemical locked inside its icy crust, every whisper of geothermal heat rising from its core, each of these pieces carries a story etched into the earliest moments of our planetary neighborhood. More than 4.5 billion years ago, the solar system was not the elegant, clockwork structure we know now. It was a swirling disk of gas and dust, the solar nebula. At its center, gravity forged the sun, a blazing sphere of nuclear fusion, but around it, the disk spun and thickened, splintering into countless rocky clumps. These clumps collided, merged, shattered, and reassembled again in a cycle that lasted millions of years. Out of these collisions emerged the building blocks of the planets, planetesimals, and eventually the gas giants, Jupiter, Saturn, Uranus, and Neptune. Europa's story begins in the shadow of Jupiter's birth. As Jupiter formed, it grew into a gravitational giant, capable of reshaping the architecture of the young solar system. Its immense gravity stirred the disk around it, creating a miniature version of the solar nebula, a circumplanetary disk where its moons would eventually be born. This disk was dense with ice, rock, and organic molecules, swirling in orbits that would one day settle into the Galilean system: Io, Europa, Ganymede, and Callisto. Europa emerged as the second major moon, forming from a mix of silicate rock and water ice. It was not yet the smooth, brilliant world we see today. Early Europa was warm, chaotic, pummeled by debris, and shaped by forces that would determine its destiny forever. During the earliest phase of its existence, Europa experienced what scientists call a magma ocean phase, a period when its interior was molten, its heat driven by both radioactive decay and the relentless bombardment of leftover rocky fragments. Impacts were constant, and each collision blasted away parts of its surface while depositing new layers of material. These impacts generated enough energy to melt subsurface ice, mix it with silicates, and create a stratified interior. Gradually, the moon differentiated. Rock sank toward the center, forming a metallic core, while lighter material, water and ice, remained above. It was during this time that Europa became an ocean world, not with a quiet, stable sea, but with a global layer of water that may have been hundreds of kilometers deep, heated by the moon's young interior. As Europa cooled, this ocean began to freeze from the top down, forming the first version of the icy crust we see today. But beneath it, liquid water remained protected, insulated, and stirred by processes that were only beginning to take shape. Meanwhile, Jupiter's gravitational influence carved the arrangement of its moons into what is known as the Laplace resonance, a precise orbital dance in which Io, Europa, and Ganymede tug on each other rhythmically. This resonance is not simply an orbital curiosity. It is the reason Europa's ocean still exists today. Every orbit, Europa experiences tidal flexing, its interior pulled and stretched by Jupiter's immense gravity. This stretching produces frictional heating, preventing the subsurface ocean from freezing solid. Without this resonance, Europa would have become a frozen moon billions of years ago. Instead, it remained geologically alive. And so, through a delicate balance of gravitational forces, thermal energy, and chemical evolution, Europa reached a moment of stability. Its surface cooled into the bright, smooth crust of water ice we see today, an ice sheet so reflective that Europa became the most luminous moon in the solar system. Beneath that shell lay a global ocean containing more water than all of Earth's oceans combined. But Europa's birth was not simply about ice and rock, it was about chemistry. During its formation, Europa inherited a wealth of materials from the circumplanetary disk. Among them were simple carbon molecules, methane, carbon dioxide, formaldehyde, along with nitrogen compounds and traces of sulfur. When mixed with liquid water and heated by the moon's interior, these molecules may have undergone a cascade of reactions, forming amino acids, hydrocarbons, and perhaps early prebiotic chemistry. Some scientists even suggest that Europa, not Earth, could have been one of the earliest potential habitats for life in the solar system. Whether or not life emerged, Europa's early environment established everything needed for habitability: liquid water, chemical building blocks, and an energy source. These conditions, formed in the first tens of millions of years, would shape Europa's entire future. Over time, the solar system settled, the rain of debris slowed, Jupiter's magnetic field intensified, radiation sculpted Europa's surface chemistry, and slowly the moon adopted the quiet, icy facade we know today, a world appearing silent and inert from the outside, but hiding a restless, dynamic ocean underneath. We now believe that Europa's ocean is in direct contact with its rocky seafloor. Hydrothermal vents may exist there, just like the vents on Earth's mid-ocean ridges, vents that, on our planet, teem with life, even in total darkness. If Europa possesses similar vents, they could stir minerals, heat water, and create chemical gradients, the driving forces behind energy-rich ecosystems. Europa's birth was, in every sense, the creation of a world designed for possibility, a world sculpted by fire, cooled by ice, and sustained by gravity, a world quiet on the outside, yet filled with movement and potential on the inside. a world that began as a frozen sphere and transformed into one of the most intriguing ocean worlds we've ever discovered. And this origin, these first chaotic chapters, set the stage for everything that would follow. Its cracked surface, its shifting crust, its hidden water, and the mysteries that continue to draw spacecraft, scientists, and dreamers toward it. And now, with the story of Europa's beginning carved into place, we can travel meaningfully into its present, into the ice, the ocean, and the silence that defines this extraordinary moon. Chapter 2: The Architecture of Ice: How Europa Became a Frozen World. If Europa's birth was a story of fire and impact, then its evolution is a story carved by ice, an ice that behaves nothing like the frozen water we know on Earth. To understand why Europa hides an ocean beneath its frozen exterior, we must first understand the strange physics shaping its shell. A shell that fractures, drifts, rotates, and flexes like the crust of a living world. Europa's surface is deceptively simple. From a distance, it looks like a white marble veined with long, rust-colored streaks. But each line, each fracture, is a record of an interior in motion. Scientists describe Europa's outer layer as a cryosphere, a sphere made entirely of frozen water, layered like a planet-sized glacier. At the very top lies a brittle crust only a few kilometers thick, constantly cracked by gravitational stress from Jupiter. Beneath that brittle shell, however, lies something profoundly different: warm, ductile ice, soft enough to flow over geological timescales. It is a realm where temperatures and pressures combine to form exotic phases of ice: Ice 2, Ice V, and Ice VI, crystalline structures that do not exist naturally on Earth but dominate Europa's internal architecture. To understand why Europa looks the way it does, we must trace the forces shaping it. These forces come overwhelmingly from Jupiter. Europa orbits Jupiter locked in a gravitational dance with Io and Ganymede, a resonance that ensures Europa's orbit is never a perfect circle. Instead, it oscillates, sometimes slightly closer to Jupiter, sometimes slightly farther away. This constant change subjects Europa to tidal flexing, stretching, and relaxing the moon's interior twice during every orbit. The consequences of this flexing are enormous. Friction inside Europa generates heat, so much heat, in fact, that an ocean remains liquid beneath tens of kilometers of ice. When that heat interacts with Europa's solid crust, the surface fractures. These fractures expand in both directions at once, carving lines called lineae that stretch for thousands of kilometers. Many of these lines are perfectly straight, as if drawn with a ruler. Others curve gently around the moon, following stresses within the ice shell, like fault lines on Earth. Each fracture fills with fresh material rising from below warm ice, slush, or briny water that quickly freezes upon exposure to open space. Over millions of years, these fractures have repaved much of Europa's surface. That is why Europa has so few impact craters. The surface is continually renewed, making it one of the youngest landscapes in the entire solar system. Even more mysterious are the chaos terrains, shattered regions where the ice appears to have broken, rotated, and refrozen in place. Here, blocks of ice the size of continents float in frozen slush like pack ice on Earth's Arctic Sea. Scientists believe these terrains form when warm material rises from below, melting or weakening the crust above it. The process may be driven by plumes of ocean water or upwellings of warm ice from Europa's interior. The existence of chaos terrains is one of the strongest clues that Europa's ocean interacts directly with its surface. But the most astonishing insight comes from measurements of Europa's magnetic field. When spacecraft like Galileo flew past the Moon, Jupiter's magnetosphere swept through Europa like an invisible tide. The Moon responded with an induced magnetic field, a kind of electromagnetic echo. This echo can only be produced if Europa contains a global, electrically conductive layer. The best candidate for that layer is a salty, liquid ocean. Not a lake, not a sea, but a planet-wide ocean, deeper than Earth's oceans combined. The mathematics tells a remarkable story. An ocean roughly 100 kilometers deep, resting beneath an ice shell around 15-25 kilometers thick. If true, Europa would contain twice as much liquid water as Earth, despite being only a quarter of Earth's diameter. We must also consider the chemistry that flows through this icy world. Europa's surface is constantly bombarded by radiation from Jupiter, splitting water molecules and generating oxidants like hydrogen peroxide. Weathering processes distribute these compounds across the icy shell. When fractures open, the oxidants can be carried downward, mixing with the ocean beneath. This means Europa's ocean may not be isolated or inert, but chemically active, replenished with ingredients essential for habitability. The dynamism of Europa's shell reveals a world where surface and interior are coupled, where energy moves from Jupiter to ice, from ice to ocean, and possibly from ocean to surface again. This cycle is one of the most important clues in the search for life. On Earth, life thrives where energy flows along ocean vents, volcanic ridges, and deep underwater fractures. Europa's surface tells us that similar processes could be happening right now beneath its frozen crust. If Europa's icy shell is the Moon's skin, then the ocean below is its beating heart. Every fracture, every ridge, every drifting plate of ice is a signal that Europa is not a silent sphere, but a world in motion, constantly reshaped by forces that never rest. And as we move deeper into Europa's story, we begin to see why scientists believe this small moon may be one of the most promising places to search for extraterrestrial life in the solar system. Chapter 3: A Shell of Ice. Why Europa froze into a world of white. To understand Europa's hidden ocean, we must first understand the shell that hides it. Europa's ice crust, stretching for thousands of kilometers yet barely dozens of kilometers thick, acts not just as a barrier, but as a geological archive. Every crack, every ridge, every faint stain of minerals trapped within the ice is a sentence in a long, quiet story of transformation. If water is Europa's secret, then ice is its memory. Europa's frozen exterior is, at first glance, shockingly smooth. Among the solar system's major worlds, only a few display so few craters. And that smoothness is not a sign of youth alone, it is proof that Europa's surface is alive, constantly reshaped by internal heat pushing from below. Ice here is not static. It flows, it fractures, it renews itself, and through that slow churning, Europa reveals the presence of something powerful beneath, an internal ocean capable of altering the entire outer shell. But Europa did not begin as a frozen world. In the earliest days of Jupiter's system, temperatures and collisions shaped the Moon into a sphere of rock and water ice. Radioactive decay and residual heat from formation warmed its interior. But the most significant source of thermal energy came from the gravitational pull of Jupiter. As Europa orbited the giant planet, its elliptical path forced the Moon into an endless cycle of flexing, stretching, and compressing its interior. This process, known as tidal heating, generates heat, the way bending a metal spoon warms it in your fingers. On Europa, however, The scale is enormous. Entire layers of the moon creak and shift under gravitational stress. Over millions of years, that heat slowly melted a vast portion of the internal ice. The exterior froze solid, but the warmth trapped underneath prevented the complete loss of liquid water. What remained was a global ocean tens of kilometers deep, sealed beneath a rigid, shining crust of crystalline ice. Europa became a world of duality, freezing cold above, liquid and potentially habitable below. From orbit, Europa's outer shell appears like a cracked porcelain sphere. Long, linear streaks called lineae cut across the surface in tangled patterns. These fractures are not merely surface scratches, they are tectonic scars. As the ice stretches and contracts, warm material from below pushes upward. The ridges and dark streaks trace the places where the crust has broken, separated, and refrozen. Some regions look as if entire continents of ice have drifted apart and rotated slightly, resembling broken plates in a frozen puzzle. Scientists believe these features prove something extraordinary. The ice shell is not tightly fixed to the rocky interior. Instead, it floats literal tectonic plates of ice drifting on a global ocean. Europa may be the only world besides Earth where plate-like movement exists, though here it is ice rather than rock that shifts and rearranges. The thickness of Europa's ice has been debated for decades. Some models propose a thin shell, only a few kilometers thick, soft enough for ocean water to occasionally burst through, carving new terrain. Other models, supported by spacecraft observations, suggest a thicker crust, perhaps 15 to 25 kilometers, that is solid but still fractured and pliable under tidal stresses. Regardless of the exact thickness, one fact remains constant: the shell is not static, it is dynamic, restless, and shaped from below. The colors on Europa's surface offer further clues. The moon's ice, naturally brilliant and white, is streaked with rusty reds, browns, and golden hues. These pigments are believed to be salts, sulfur compounds, and minerals carried up from the ocean below or deposited by Jupiter's volcanic moon Io. When these materials mix with sunlight and radiation, they change color, acting like chemical fingerprints. Each rare shade suggests a different type of chemistry at work beneath the shell, hinting at the ocean's composition. One of the most intriguing possibilities is the presence of magnesium sulfate, a mineral similar to Epsom salt. Others include sodium chloride, the very salt that flavors Earth's oceans. If Europa's ocean is salty, it suggests that liquid water interacts with the rocky mantle below, a key ingredient for complex chemistry and possibly biology. Europa's ice shell may also behave like a semi-transparent lens. Beneath certain regions, heat from the ocean warms the underside of the crust. Warmer ice becomes softer, more ductile. This allows slow cycles of convection and upward and downward flow of the ice layer. These convection cells could explain the presence of chaos terrain, fractured landscapes that appear broken, rotated, and refrozen. Large blocks of ice drift and tilt like giant rafts, directed by forces from below. Chaos terrain may represent areas where the ocean comes closest to the surface. In some cases, the ice might even melt through temporarily before refreezing, forming lakes trapped within the crust itself. If these lakes exist, they could act as transition zones, mixing chemistry from both the ocean and surface. In planetary science, such interfaces are considered prime environments for complexity and possibly life. Yet despite all this activity, Europa remains silent. There are no volcanoes, no storms, no winds to sculpt its landscape, only the slow, invisible force of Jupiter's gravity shapes its destiny. This icy shell is not dead, it is continuously shifting, responding to internal and external pressures in an intricate, rhythmic cycle. Beneath the quiet, Europa works. Its surface disguises the intensity below, acting as a cryptic mask for what could be the most Earth-like ocean in the solar system. Deeper than any ocean here, darker than any abyss, and older than any sea that has touched Earth's shores. Understanding Europa's ice shell is crucial because every clue locked within it tells a part of a larger story, the story of a world where freezing cold protects the possibility of warmth, where ice shields a restless ocean, and where the silence of the surface might hide the stirring of something alive. And to decode Europa fully, we must continue deeper, not just into its structure, but into the tensions and forces that shape it from both above and below. Chapter 4: The Ice Shell, a planet-sized time capsule. From orbit, Europa looks deceptively simple, an ivory sphere etched with reddish fractures, as if a cosmic hand once dragged a quill across its frozen surface. But simplicity is an illusion, and as we move deeper into Europa's silent story, we reach one of the most intricate structures in the entire solar system, its ice shell, a global carapace that behaves like both stone and water, both shield and storyteller, both mirror and mask. The ice shell is not just a surface. It is a recording device, one that has been archiving Europa's history for billions of years. To understand Europa, we must understand this ice, a shell suspended between two worlds. Europa's ice crust is estimated to be 15 to 25 kilometers thick, though some regions may be far thinner, perhaps just a few kilometers, where tidal stresses stretch the crust like warm toffee. This shell sits atop a global ocean at least 100 kilometers deep, more water than all of Earth's oceans combined. But unlike Earth's rigid crust, Europa's ice shell is not a fixed structure. It is a dynamic frontier, constantly shifting under the influence of Jupiter's gravitational pull. The result is a world of slow motion, cracking, bending, flexing, groaning, a cryogenic ballet that never stops, even though Europa makes no sound. The ice shell, in a physical sense, is Europa's middle realm. Above it, vacuum, radiation, and the frigid silence of deep space. Below it, a warm, dark ocean teeming with chemical potential. Between the two lies this frozen barrier, an archive of the moon's past, and a gatekeeper of its future. The language of fractures. If Europa has a written language, its alphabet is carved into its surface. The moon is covered with long, reddish-brown streaks that stretch for hundreds, sometimes thousands of kilometers. These features are among the most distinctive in the solar system, and their geometry tells a story of planetary scale stress. Some lineae run parallel for great distances, like railroad tracks built by geologic forces. Some intersect at sharp angles, forming patterns that resemble fingerprints. Others appear offset, evidence that sections of Europa's crust have drifted sideways, much like Earth's tectonic plates. But unlike tectonic plates on Earth, Europa's motion is not driven by internal heat alone. It is powered by the constant gravitational kneading from Jupiter and its fellow moons Io, Ganymede, Callisto, a gravitational choreography that stretches and compresses Europa's surface like a breathing lung of ice. To planetary scientists, these cracks aren't scars. They are seismographs, records of the forces deflecting, twisting, and flexing the crust. Every line is a measurement. Every fracture is a timestamp. Chaos terrain, the frozen evidence of subsurface upwelling. Among Europa's most fascinating features are regions known as chaos terrains, jumbled landscapes where ice blocks sit tilted, rotated, or embedded in refrozen slush. To understand them, imagine an ancient sheet of Arctic sea ice shattering and rearranging after an under-ice plume of warm water rises and melts it from below. Europa's chaos regions suggest something remarkable. Warm water from the global ocean may occasionally breach the shell, rising toward the surface before freezing again. This implies that Europa's ice shell is not just a passive crust. It may be porous in spirit, leaking heat, brine, and chemistry upward in slow bursts. Some chaos terrains, such as Connemara chaos, look like frozen shipwrecks, broken plates of ice, drifting apart, then recongealing, forming puzzles that no longer fit perfectly. These regions are considered prime targets for future landers because they may capture fresh material from the ocean below, frozen snapshots of Europa's deep interior. Salt, sulfur, and the colors of a distant ocean. The ice is not pure. Throughout Europa's surface, reddish streaks and patches contaminate the white crust with hues reminiscent of rust and clay. These colors come from materials embedded within or erupting through the ice. A mixture of hydrated salts, sulfuric compounds, and irradiated molecules. Scientists believe that some stains originate from the ocean below, carried upward through cracks. Others come from Io's volcanic ejecta, sulfur and dust blasted into space by the most volcanic body in the solar system. Jupiter's radiation bakes and rearranges these materials into new compounds, giving Europa its signature palette. This interplay, ocean chemistry below, radiation chemistry above, turns the ice shell into a planetary chemistry lab. The cracks are not just fractures. They are delivery systems for molecules. They are pathways for exchange. Every red streak is a sign that Europa is not sealed shut. It is communicating between layers. The ice shell is a planetary shield. Europa orbits deep within Jupiter's radiation belts. The surface receives doses of high-energy particles that would sterilize most environments known on Earth. Without protection, the ocean below would be exposed to relentless radiation. The ice shell prevents this. Even a few meters of ice would shield the ocean. Europa has tens of kilometers. It is a barrier thick enough to protect molecules that could form life, chemical gradients that power metabolic processes, liquid water maintained by tidal heating. This makes Europa unique. It is a world where habitability exists beneath a surface that is utterly hostile, a paradox sculpted by physics, sustained by motion, preserved in ice, seismic clues, and the internal structure. Europa's ice crust may experience icequakes, fractures that ripple through the shell as Jupiter's gravity flexes the moon. Future missions like NASA's Europa Clipper hope to detect these vibrations. Seismic waves could reveal the thickness of the ice, the depth of the ocean, and the presence of subsurface lakes trapped within the crust. Some scientists speculate that Europa may contain water pockets, intermediate reservoirs between the surface and the deep ocean, similar to the lakes beneath Antarctica's ice sheets. If such lakes exist, they might represent environments where water interacts directly with the ice above, creating zones of enhanced habitability. A shell that may drift over time. Europa's surface may not be anchored to its core. It may slide like sea ice drifting atop Earth's polar oceans. moving slowly over the subsurface water. If true, Europa's crust could undergo true polar wander, a process where the entire outer shell reorients over time due to internal redistribution of mass or external gravitational forces. This would mean that features on Europa's surface could migrate over geological timescales, carrying chaos terrains and crack systems along paths that trace the Moon's internal evolution. The idea that an entire planetary shell may drift is astonishing. A world whose skin can glide across its liquid heart. The ice shell as a gateway to the ocean. The true wonder of Europa's ice shell is that it is not simply a barrier. It is a potential access point to the ocean below. Jets of water vapor have been tentatively detected erupting from Europa's surface, similar to the geysers on Saturn's moon Enceladus. If confirmed, these plumes would allow spacecraft to sample the Moon's ocean without drilling through kilometers of ice. Even tiny cracks could permit exchange of salts, organics, thermal energy, oxidants generated by radiation. This means Europa's ocean is not isolated. It breathes slowly, silently, through its frozen shell. Closing the chapter, the ice shell of Europa is not merely a crust. It is a world unto itself, dynamic, fractured, expressive, and alive with the physics of tides and temperature. It records Europa's past. It shapes Europa's present, and it moderates the possibilities of Europa's future. Now that we understand the skin of this frozen world, we can descend further into the chemistry, heat, and deep structure that define what lies beneath. Chapter 5: The Shell That Never Sleeps, Europa's Dynamic Ice Crust. If Europa's hidden ocean is the heart of the Moon, then its ice shell is the skin, a shifting, cracking, ever-moving interface between the frozen surface and the global sea beneath. And unlike the frozen lakes on Earth that remain still through winter, Europa's ice crust is alive with stress, tension, flexing, and constant reshaping. It is a boundary layer under pressure, sculpted not by weather, but by the gravitational hand of Jupiter. Europa's smooth, bright exterior is one of the most deceptive surfaces in the solar system. Seen from afar, it resembles a pristine marble dipped in soft white light. Up close, it tells a different story. Long fractures stretching thousands of kilometers, ridges that rise like frozen tidal waves, chaotic terrains where the crust shattered and refroze, and patches where the ice appears to have rotated as if floating on a viscous sea. This chapter explores the mechanics behind that restless shell, how it forms, how it moves, and why it provides some of our best clues about the ocean concealed below. A crust sculpted by tides, not seasons. Europa is far too cold for sunlight to melt the surface. The temperatures average 160 degrees Celsius, and daytime warmth does little more than soften the uppermost grains of frost. But Europa's true source of energy lies deep within its orbital dance. Jupiter's gravity pulls on the Moon with enormous force, while the gravitational nudges from Io and Ganymede constantly change the shape of Europa's orbit. This stretches the Moon slightly on each cycle, causing its entire body from the core to the surface to flex by up to 30 meters. To put that into perspective, Earth's tides move the oceans by meters. Europa's tides move the ground. This rhythmic flexing creates frictional heat within the interior. Most of that heat maintains the subsurface ocean in a liquid state, but some of it climbs upward into the ice shell, warming its base to near melting temperatures. This creates a layered structure, a brittle outer crust, a warmer and more ductile mid-layer, and a nearly slushy base. The result is an icy world where the surface fractures, shifts, and rotates slowly over time. The cracks that cross a world. Europa's iconic features are the lineae, long, dark streaks that crisscross the surface. Some are thin and sharp, like scratches on porcelain. Others are thick, double-ridged structures rising hundreds of meters above the surface. These cracks form when the crust responds to tidal stresses. As Europa stretches or compresses, the brittle ice near the surface breaks open. Briny water or slushy ice may rise into the gap from below, freezing in place and leaving behind darker, mineral-rich streaks. These lineae serve as geological fingerprints. By analyzing their distribution and direction, scientists can map the history of Europa's tidal cycles, measure how the crust has rotated over time, and infer the thickness of the ice. Some lineae appear remarkably fresh, meaning Europa's surface is continually renewed. Crater counts suggest the entire crust could be less than 50 million years old, a blink in geological time. This means Europa is resurfacing itself, erasing old features and creating new ones. And a world that resurfaces is a world with active geology and possibly active ocean circulation. Ridges, frozen evidence of a rising sea. Among Europa's most intriguing features are the double ridges, parallel walls of ice separated by a central trough. Some ridges stretch thousands of kilometers. These structures may be the result of repeated cycles of cracking and refreezing. When a fracture opens, warm, salty water might rise into it. As Europa cools through its long night, the water freezes, expands, and pushes the walls of the fracture upward. Over millions of cycles, the ridge grows taller. Recent research from NASA's Europa Clipper mission suggests that these ridges may form much like seasonal cracks on Arctic sea ice on Earth. If true, it implies Europa's ice crust is extremely thin in some regions, perhaps just a few kilometers thick, making surface-to-ocean exchange far easier than previously believed. Thin ice means a more dynamic world. Thin ice means easier transport of nutrients. Thin ice means the ocean is not isolated, but breathing. Chaos terrain, the surface that collapsed and reborn. Perhaps the most dramatic evidence of an active shell is the presence of chaos terrains, vast, jumbled landscapes where the surface seems shattered into rotating blocks. These regions resemble icebergs trapped in slush. A leading theory is that warm water from below partially melted the crust in these areas, causing surface plates to break apart and drift before refreezing in new configurations. One famous example, Connemara chaos, showcases broken blocks ranging from small segments to fragments, dozens of kilometers across. This suggests that Europa's ice shell can be locally weakened, fractured, and rearranged, proof of upward heat flow from the ocean. Chaos terrains may also indicate the presence of subsurface lakes, pockets of water trapped within the ice shell itself. These shallow reservoirs could be only a few kilometers beneath the surface, and where water is close to the surface, chemistry and energy become far more complex and interesting. Surface chemistry, a window into the deep. Although Europa's shell separates us from the ocean, it also preserves traces of the chemistry below. Spectroscopic observations have revealed salts, including magnesium sulfate and sodium chloride, spread across the surface. Some appear concentrated along cracks and ridges, implying they were transported upward by water. The coloration of lineae, chaos regions, and certain patches may be tied to irradiation of these salts by Jupiter's powerful magnetic field. This radiation chemistry generates darker, rust-colored materials unlike anything found on Earth's polar ice. Understanding these compounds helps scientists infer the ocean's salinity, pH, and mineral content. Europa's radiation environment is harsh, but it acts like a giant chemical processor. What rises from the ocean is transformed on the surface. What forms on the surface may fall back down through cracks. The crust is not just a barrier, it is an active chemical reactor bridging two worlds. Slow motion drift, the shell that may rotate freely. One of the most surprising revelations about Europa is the possibility that its ice crust rotates independently from the rocky interior. This non-synchronous rotation occurs because tidal forces push and pull the shell in slightly different directions from the ocean and core. Over time, the crust may drift like a detached plate, slowly shifting longitude by tens of degrees over millions of years. If true, this suggests a deep decoupling between the ocean and the crust. It means Europa's shell is not rigidly locked to the moon's core, but afloat. And that floating nature makes surface to ocean exchange far more dynamic. Europa's icy shell may behave like continental plates drifting over Earth's mantle, but slower, colder, and driven not by heat but by Jupiter's relentless gravity. The shell as a scientific target. For future missions like Europa Clipper and JUICE, the ice crust is not a barrier, it is a data archive. It records the history of tidal heating, the distribution of internal stress, the chemical connection to the ocean, the thermal variations across latitude, the presence of shallow water pockets. By scanning the shell with ice-penetrating radar, measuring its thickness with gravity mapping, and analyzing its chemistry with spectrometers, scientists can read Europa's surface like a chronicle of its inner workings. The shell is the interface where Europa's mysteries become accessible. Chapter 6: The Cracks That Speak. Europa's fractured skin as a geological recorder. Europa is one of the few places in the solar system where silence is misleading. From orbit, its surface looks calm, smooth, pale, crossed by long dark lines that resemble ink strokes on ivory. But beneath that quiet facade, Europa's crust is moving, pulling, stretching, and healing in ways that no other moon in the Jovian system can replicate. If the ocean beneath is Europa's hidden world, then the cracks on its icy skin are its language, recording every force that has acted upon it for millions of years. To understand Europa, scientists first learned to read these fractures the way geologists on Earth read fault lines, sediments, and mountain belts. And what the cracks reveal is a world that is anything but still. The surface, a planetary palimpsest. Europa's ice shell averages between 15 and 25 kilometers thick. But what makes it remarkable is how young it is. While most moons like Callisto or our own moon are coated in impact scars billions of years old, Europa's surface is nearly pristine. Craters are rare, their absence telling a story far louder than their presence. Europa renews itself. The fractures across its surface are not random. They form patterns, some nearly global, that reflect stresses generated deep within Europa's interior. Jupiter's tidal pull stretches the moon as it orbits in an elongated path. The stress doesn't simply create cracks, it organizes them. Some run for thousands of kilometers, clean and sharp. Others curve around the poles or slice across plains of blue ice. If Europa had continents, these fractures would be its tectonic boundaries. Geophysicists noticed something peculiar early on. Many of Europa's lines shift. A crack seen in one Voyager image reappeared in a later Galileo image. but slightly offset, as if sections of the ice crust had drifted. This drifting behavior is one of the strongest clues that Europa's ice shell is floating atop a liquid layer. The surface is not anchored, it is drifting on a sphere of water. Cycloids, the moon's arc-shaped mysteries. Among Europa's most intriguing features are its cycloidal cracks, long chains of arc-shaped segments that curve gently like waves frozen mid-motion. No other world in the solar system shows fractures quite like these. For decades, scientists debated their origin. Were they caused by impacts, cryovolcanism, changes in surface temperature? The answer was found in mathematics. Europa's orbit has a slight eccentricity, meaning tidal stress on the ice changes direction as Europa rotates. Over time, the stress field sweeps across the surface. When the stress direction rotates gradually while the ice remains brittle, it produces a fracture that curves continuously, exactly like the cycloids we see today. In laboratory simulations, similar patterns appear in brittle materials flexed repeatedly under oscillating loads. Europa's surface behaves the same way, but on planetary scales. These icy arcs reveal that Europa is not geologically dead. It flexes, it groans, it responds to Jupiter's pull like a living body. Strike-slip faults, Europa's version of Earth's San Andreas. Another striking discovery was evidence of strike-slip faulting, similar to the tectonic behavior of Earth's crust along the San Andreas Fault. In these cases, two blocks of ice slide horizontally past one another, sometimes by kilometers. This implies the ice shell is mechanically strong, not fragile frost. Europa experiences stress comparable to small terrestrial tectonic plates. The shell may be decoupled from the ocean beneath, allowing it to shift independently. In other words, Europa's crust is not simply cracking, it's tectonically active. This raises a deeper, more profound question. If the ice shell behaves like tectonic plates, does Europa host a form of ice plate tectonics, a process unheard of elsewhere in the solar system? Some models support this idea, others propose that the ice convects slowly, similar to Earth's mantle. Either way, the conclusion remains: Europa is dynamic, not dormant. Chaos terrains, places where the surface failed. Europa's most enigmatic features are its chaos terrains, regions where the surface appears shattered, rotated, and refrozen like broken sea ice that refroze overnight. These areas suggest a dramatic process. Heat rises from below, perhaps from tidal flexing or hydrothermal plumes. The ice shell thins from the bottom, weakening structural support. Sections of the surface collapse, tilt, float, and drift. Ocean water or slush wells upward, flooding the region. Eventually, the water refreezes, preserving the chaos like a geological snapshot. Some chaos terrains stretch hundreds of kilometers, hinting at enormous upwellings of heat. They may represent regions where the ocean and surface briefly interacted, making them prime landing sites for future spacecraft, searching for chemical signatures of life. Ridges and double ridges, Europa's most common feature. Europa is covered with double ridges, pairs of parallel walls separated by a central trough. Some reach 300 meters high, taller than Earth's largest sand dunes. Their origin remained unsolved until 2022, when researchers studying Greenland's ice sheet discovered a nearly identical structure forming above a pocket of pressurized water. This breakthrough revealed a likely mechanism. Liquid water or slush rises from below. Pressure pushes upward, lifting the ice. As the water freezes, it expands, creating ridge walls. Repeated cycles build the structure higher and wider. If this mechanism also happens on Europa, then it suggests that liquid water frequently approaches the surface, or at least circulates through the shell in semi-liquid pockets. This is incredibly important. It means Europa's surface is not just ice over water, it is a membrane through which the ocean's chemistry can migrate. If life exists beneath the ice, these ridges could carry its chemical traces toward the surface. The cracks as records of Europa's tides. Every fracture, ridge, and displacement on Europa encodes a precise moment in its tidal history. By mapping them, scientists can reconstruct past orbital cycles, shifts in Europa's rotational axis, episodes of intense tidal heating, regions of rising or sinking ice, the strength and location of subsurface water pockets, the thickness of the ice shell at different times. Europa's surface is young not because it is calm, but because it is constantly rewritten. It is a palimpsest, a surface where older stories are erased and new ones carved by Jupiter's gravitational pull. What the cracks tell us about the ocean below. The surface is not just a record of ice mechanics, it is a mirror of the ocean beneath. The cracks imply the ocean is deep up to 100 kilometers. The ice shelf floats and moves independently. Heat from tidal flexing travels upward into the ice. Liquid water exists close to the surface in many regions. The ocean must be global, not regional. The ocean interacts with the crust through convection and fractures. In short, Europa's ice moves because the ocean moves. The two are inseparably linked. The ocean shapes the crust from below. Jupiter shapes it from above. The cracks capture the moment where those forces meet. Chapter 7: The Hidden Architecture of Europa's Ice Shell. If Europa's ocean is its beating heart, then the ice shell above it is the living membrane through which the moon communicates with space. Far from being static or frozen in geological stillness, Europa's ice behaves like a planetary-scale organism, stretching, cracking, migrating, and reshaping itself through the quiet mechanics of physics. To understand Europa as a world, we must understand its shell. 1. The ice is not a barrier, it is a dynamic system. For decades, scientists believed Europa's ice crust was a single, solid shield, tens of kilometers thick. But as spacecraft images grew sharper and gravity measurements more precise, a different story emerged. Europa's ice shell is mobile, flexible, and constantly evolving. It is neither a rigid wall nor a passive lid. It is a dynamic interface where heat, salt, radiation, and internal energy all intersect. The system is shaped by 4 forces: tidal flexing from Jupiter's gravity, heat movement from the ocean below, fracture propagation from surface stresses, radiation-driven chemistry at the surface. These forces sculpt the ice into a world of ridges, rafts, bands, and chaotic terrains, each one preserving a geological timestamp. 2. The surface cracks like glass, but moves like clay. The most striking feature of Europa's surface is its global network of fractures, thousands of kilometers long, some stretching across entire hemispheres. But unlike the brittle cracks of rock, Europa's fractures behave like fractures in a material that is neither fully solid nor liquid. Europa's ice is strong on short timescales, ductile on long timescales, mobile when warmed, brittle when cooled. This duality creates patterns that resemble broken glass, tectonic plates, drifting sea ice, braided river deltas, Every pattern reveals a different mode of stress and movement. Converging ridges. These form when the ice shell compresses, forcing slabs upward into paired ridges, sometimes hundreds of meters tall. They are signs of crustal convergence, similar to Earth's mountain-forming zones but governed by ice, not rock. Diverging bands. Other regions stretch apart, creating long, dark bands where fresh ice wells up from below. This resembles mid-ocean ridge spreading on Earth, except Europa is doing it with frozen water instead of basaltic magma. Chaos terrains. Some of the most mysterious landscapes on Europa appear as disrupted regions filled with jumbled blocks resembling shattered icebergs locked into place. These terrains are believed to form when pockets of water or slushy brine rise into the shell and partially melt it from within. Each chaos region could be evidence of subglacial lakes, temporary melt pockets that freeze and refreeze over thousands of years. 3. A shell that rotates differently from the Moon. One of the most intriguing discoveries from Galileo spacecraft data was that Europa's ice shell may rotate at a slightly different speed than the Moon's interior. This process is called non-synchronous rotation. Imagine a shell so loosely coupled to the ocean beneath it that it can slide slowly over the underlying layers, drifting over centuries like a planetary-scale tectonic plate. If true, this phenomenon would explain why some fractures do not align neatly with predicted tidal stress patterns. It also suggests that Europa's ice shell is mechanically decoupled, globally mobile, affected by ocean circulation beneath. In other words, Europa's surface might slowly drift above its own hidden ocean, moving across the globe like the skin of a living organism. 4. Heat rises from below and reshapes the crust. Europa's ocean is warm compared to the surface. Even a few degrees of temperature difference creates convection currents within the ice. Heat rises from the ocean upward in 3 key ways. Thermal convection. Warm ice becomes less dense and rises, while cold ice sinks, just like magma in Earth's mantle. Tidal dissipation. The constant flexing of Europa's crust generates frictional heating, especially along fractures and at depth. Cryovolcanism. Briny water may sporadically intrude upward into the ice, freezing into new layers. The result is an ice crust that behaves more like a circulating fluid than a solid block. The shell may host ice tectonics. Instead of rock tectonics, Europa may host ice tectonic cycles where new ice rises, old ice sinks, fractures propagate, surface slabs migrate, ocean messages travel upward as thermal plumes. This would explain the relative youth of Europa's surface. There are few impact craters, meaning the shell renews itself over millions, not billions, of years. 5. Radiation creates chemistry at the surface. Europa orbits inside Jupiter's intense radiation belt. High-energy particles slam into its surface, breaking apart water molecules and generating hydrogen peroxide, molecular oxygen, sulfate compounds, oxidants. These oxidants accumulate in the ice and snow. If they are transported downward into the ocean through fractures or melt pockets, they could provide chemical energy sources necessary for life. Europa's radiation environment, though harsh, may indirectly support habitability by driving the chemistry needed for life in the ocean. This creates an extraordinary planetary system, a frozen surface constantly bombarded by radiation, overlying a warm ocean kept alive by tidal forces, connected only through fractures. thermal upwellings, and chemical cycling. 6. The ice shell. As a gateway to the ocean. Europa's shell is often described as a barrier, but that is a misconception. It is a gateway, a dynamic, porous, chemically active system that transports heat, minerals, oxidants, water, energy between the surface and the depths. This exchange is crucial. Without it, Europa's ocean could stagnate, become chemically uniform, and lose its potential for life. Instead, Europa exhibits every sign of being a world with active chemical cycling, where the ice shell acts like a planetary lung, breathing energy downward and bringing oceanic activity upward. 7. What the ice shell tells us about Europa's past. Europa's surface patterns act as a chronological archive. By studying the orientation, age, and distribution of ridges and bands, scientists can reconstruct the Moon's recent history, where the shell once thinned, where convection occurred, how the ocean circulated, how Jupiter's tidal forces shifted over time, where melt pockets formed and froze again. The shell contains stories written in fracture lines and frozen flows, stories of heating events, tidal stress cycles, global reorientation, and possibly even ancient cryovolcanic eruptions. Just as geologists read Earth's crust for clues to its past, planetary scientists read Europa's ice for clues to the evolution of its hidden ocean world. 8. In the end, the ice shell is the key to everything. Europa's habitability does not depend solely on its ocean. It depends on the interaction between ocean and ice, and the ice shell is the medium through which this interaction becomes visible to us. It tells us where heat escapes, where chemistry evolves, where the ocean reaches upward, where the surface fractures downward, where future missions should land. Without the ice shell's unique behaviors, its ability to move, flex, fracture, and cycle materials, Europa might be just another frozen moon. But it isn't. Europa is alive with motion. Its ice is active. Its ocean is heated. Its chemistry is evolving. Its surface is rewriting itself in near real time on geological scales. And the shell, silent, bright, and restless, is the most important clue we have to understanding what lies beneath. Chapter 8. The Architecture of Europa's Tectonic Skin. If Europa's subsurface ocean is its beating heart, then the icy shell above it is the shifting, groaning skeleton that reveals everything happening underneath. By the time we reach this chapter of Europa's story, the moon no longer looks like a silent marble floating beside Jupiter. It becomes clear that its fractured surface is a geological tapestry, one created not by mountains, volcanoes, or rivers, but by the constant tension between ice and the ocean pressing gently from below. And as we shift from the microscale structures of its salt-rich surface to the global-scale behavior of its icy crust, Europa's outer shell reveals itself as something remarkable. A tectonic world not of rock, but of ice. 1. A planetary skin under pressure. Europa's ice crust is estimated to be between 15 and 25 kilometers thick, though some regions might thin to just a few kilometers. But unlike Earth's crust, which is rigid and anchored to solid mantle, Europa's crust floats on a vast ocean. Because of this, the entire shell behaves like a planet-sized lid drifting over warm salt water. The pressure from below isn't violent or explosive. It is steady, patient, thermal. Imagine the ocean slowly delivering heat toward the base of the crust, softening it, thinning it, creating weak points where the ice begins to bulge upward. These broad, gentle rises are known as domes, and they are one of Europa's quiet geological signatures. Scientists believe they form where warmer pockets of ocean push upward, introducing enough buoyancy to deform the overlying ice without breaking it entirely. Every dome is a reminder Europa is alive with internal motion. 2. Ridges, the frozen equivalent of tectonic rifts. Europa's most iconic features are the double ridges, pairs of raised icy spines stretching for hundreds and sometimes thousands of kilometers across the moon's surface. Some are only a few meters tall, others rise as high as a multi-story building. These ridges likely form in several stages. Tension, the ice shell stretches due to tidal forces from Jupiter. Cracking, fractures open like silent fault lines. Upwelling, warm slush or briny water from below infiltrates the cracks. Freeze back, the water refreezes, expanding and building raised walls. The result is a pattern of ridges that resemble scar tissue, a history book written in frozen fractures. Unlike Earth's volcanoes or earthquakes, Europa's activity doesn't explode, erupt, or roar. It creaks, it shifts, it freezes. Everything is slow and everything is quiet. Yet across the entire moon, these movements tell a single, consistent story. Europa has tectonics, cryotectonics to be exact. 3. Chaos terrain, where the ice breaks apart entirely. Perhaps the most dramatic expression of Europa's tectonic skin is the regions known as chaos terrain. From orbit, they appear as jagged clusters of broken blocks, some rotated, some tilted, some drifting apart like a shattered mosaic refrozen in place. To understand their formation, imagine icebergs breaking from an Antarctic shelf, drifting into the ocean, then freezing again. Now scale that behavior to a worldwide crust and replace liquid water with slush that freezes from the bottom upward. Here is the leading theory. Warm water rises from the subsurface ocean. It melts patches of the lower ice crust. The surface above loses support and collapses into the slush. The blocks drift, rotate, and refreeze. Chaos terrain is Europa's way of exhaling, briefly exposing its internal heat to the surface before sealing itself again. Some scientists believe chaos terrain marks places where the ocean once reached very close to the surface, possibly within meters. If true, these zones would be among the most promising locations for future landers seeking biosignatures. 4. Strike-slip faults, ice moving sideways. Europa's tectonic activity doesn't only involve stretching and melting, it also includes lateral movement, similar to Earth's San Andreas Fault. Certain fractures show signs of strike-slip motion, meaning two blocks of ice slid past one another. High-resolution images reveal where lines that should align are offset, indicating past motion. Modeling suggests that these motions occur due to the complex interplay of Jupiter's gravity, orbital resonances with Io and Ganymede, changes in Europa's rotational orientation, the floating nature of its ice crust. On Earth, such movements can generate massive earthquakes. On Europa, they generate icyquakes, silent but powerful shifts that propagate through the crust and send pressure waves into the ocean below. If life exists beneath the ice, these tectonic rhythms might be one of the major energy sources sustaining it. 5. Subduction. Does Europa recycle its crust? One of the most profound questions in planetary science is whether Europa has a system similar to subduction, where older ice is pushed downward and recycled into the warm interior. Evidence suggests some regions show signs of plates converging. Others contain unusual troughs where surface material seems to have been pulled downward. Ridges sometimes disappear at boundaries that resemble subduction zones. If Europa truly recycles its crust, it would be the first known example of ice tectonics with full recycling. On Earth, tectonics and volcanic recycling help regulate climate and drive chemical exchanges crucial for life. If Europa has anything similar, its internal ocean becomes even more likely to host long-term, stable habitability. 6. The constant pull of Jupiter. None of these processes happen in isolation. Jupiter, the giant, the tidal engine continuously pulls and flexes Europa in an orbital rhythm that never ends. As Europa orbits, the side facing Jupiter is pulled outward, the far side is stretched. Its interior warms through tidal heating, the same process that keeps Io volcanic, but gentler and colder. This rhythmic distortion fractures the ice and drives tectonics approximately every orbital cycle. Over millions of years, the effect is cumulative. Ridges become planetary scale stretch marks. Chaos terrains accumulate like geological bruises. Subduction-like zones emerge at converging plates. New ice rises to replace old ice, rejuvenating the surface. Europa's surface appears extraordinarily young, likely less than 90 million years old, extremely recent by geological standards. Tectonic activity refreshes the crust continually, erasing impact craters and rewriting the moon's exterior. In essence, Europa's surface behaves like a living membrane. 7. What the ice shell tells us about the ocean beneath. Each fracture, ridge, and chaotic block of ice is a clue to the world below. Tectonic patterns tell scientists where the ice is thick, where the ocean is pushing upward, how heat is distributed, where chemical exchange might occur, and where future missions should land. The ice crust is not a barrier hiding the ocean, it is a record of it. And as the evidence accumulates, one idea becomes increasingly clear. Europa's ocean is dynamic, not dormant. The tectonic shell above it is the proof. 8. A surface that behaves like an interface. Europa is one of the few places in the solar system where the boundary between the surface and the interior is actively communicating through physical processes. It is not simply a lid, it is an interface. Where Earth has volcanoes and hydrothermal vents, Europa has fractures that expose fresh ice, tectonic zones where chemicals are cycled, chaos regions where ocean water nearly touches space, heat-driven upwelling that reshapes the crust. The ice shell is a medium of exchange, a translator between oceanic physics and surface geology. 9. The silent power of an icy world. Every structure on Europa's surface whispers the same truth. This world, though quiet and cold, is alive with internal tension. A tension that does not erupt or explode, but stretches, melts, shifts, and refreezes. If Europa's ocean hosts life, it is this tectonic rhythm that keeps the world habitable, cycling chemicals, releasing heat, and stirring nutrients through the waters below. Europa is not static. It is not frozen in the way dead worlds are frozen. It is a moon that moves, a world that breathes, a shell that bends but does not break. And beneath that shell lies an ocean waiting to be understood. Chapter 9. Tides of Energy, the hidden pulse of Europa. The deeper we venture into Europa's silent underworld, the more one truth becomes undeniable. This moon is not just shaped by gravity, it is powered by it. If Chapter 8 revealed the immense pressure and unimaginable forces acting upon the ice shell, then Chapter 9 turns our attention inward toward the rhythmic, ancient energy system that drives the entire body of Europa. Tidal heating, a process as old as the solar system itself and as persistent as the orbit of a moon around a planet. It is the engine that keeps Europa alive, the silent pulse that prevents its ocean from freezing solid, and the invisible sculptor of its geological features. Europa is, in every sense, an ocean world built by tides, a dance locked in gravity. To understand the tides of Europa, we must begin with its orbit, not circular, not smooth, but slightly elongated, stretched by the powerful gravitational influence of Jupiter. This giant planet, more massive than all other planets combined, exerts a pull so strong that Europa is constantly being tugged forward and backward as it travels around it. But the story becomes even more dramatic when we consider Europa's siblings, Io and Ganymede. Together, the three moons are locked in what astronomers call a Laplace resonance, meaning their orbits reinforce each other in a perpetual gravitational rhythm. For every one orbit Europa makes, Io completes 2 orbits, and Ganymede completes 1/2 an orbit. This resonance prevents Europa from settling into a perfectly circular path. Jupiter's gravity stretches the moon, then releases it over and over like a cosmic heartbeat. The result? Europa flexes constantly, imperceptibly, but powerfully, and with each flex, its interior heats up, the physics of a warm heart. Tidal heating is one of the most fascinating and misunderstood phenomena in planetary science. When Europa is closest to Jupiter, the giant planet pulls harder on its near side than its far side. When Europa moves farther away, the pull eases. This continual change in gravitational strength bends and twists Europa's interior. Imagine bending a piece of metal back and forth. It warms. Europa does the same, except on a global scale. Inside its icy shell, crystals shift, fractures open and close, layers of ice grind past one another, and the deeper ocean sloshes in response. Every motion produces friction. Every frictional moment generates heat, and over millions of years, that heat accumulates into a stable, warm, subsurface ocean. It is, effectively, a planetary furnace powered by gravity, heat that flows like a slow tide. But tidal heating does not distribute evenly across Europa. Some regions absorb more stress, some less. Scientists believe this uneven distribution creates thermal hot lanes, pathways where warmer ice gradually rises toward the surface. These temperature gradients may explain several of Europa's signature features: cycloidal cracks that trace graceful arcs across the ice, linear fractures stretching thousands of kilometers, chaotic terrains where the crust collapses into disordered plains, reddish streaks that may be formed by salts brought up from the deep ocean. Each one is a geological map of Europa's internal tides. Even now, Europa's surface is estimated to shift by up to 30 meters every orbit, flexing like a breathing organism. Viewed from afar, Europa seems frozen, but beneath, it is a world in perpetual motion. Ocean in motion, the sloshing world below. The subsurface ocean is not a static, silent body. It moves. The tidal tug-of-war creates global currents beneath the ice, circulating energy through the water like a planetary bloodstream. Models predict strong currents near the base of the ice, vertical convection plumes rising from the deep, warm water upwellings capable of thinning the ice shell, and cold brine sinking like slow-moving snowfall. These patterns mirror processes seen in Earth's oceans, but on Europa, they are driven not by wind or sunlight, but by gravity and motion alone. It is, quite literally, an ocean stirred by forces from the heavens. If life exists there, tidal heating is its source of energy, not sunlight, not volcanic vents, just the quiet pull of Jupiter's massive hand, seafloor stress and hydrothermal possibilities. As Europa flexes, the seafloor beneath the ocean experiences its own tides. The rocky mantle stretches and compresses just like the ice shell, creating frictional heat deep inside the moon's interior. This has led scientists to propose a stunning possibility. Europa may have active hydrothermal vents at the bottom of its ocean. The same kind of vents on Earth's ocean floors, black smokers and alkaline chimneys are overflowing with chemical energy and life. Entire ecosystems exist there without a single ray of sunlight. Europa may host similar environments, minerals dissolving into hot water, chemical gradients forming rich energy sources, a warm seabed supporting complex organic chemistry. This is why Europa is considered one of the best places in the solar system to search for life. Tidal heating is not just a mechanism of motion, it is a mechanism of habitability. Faults, fractures, and whispering ice. As heat rises from the depths, Europa's ice shell responds with creaks, rumbles, and silent fractures. Though Europa has no atmosphere to carry sound, the physics of its ice tells a story. When the ice warms, it lifts, it thins, it cracks in long, straight lines. When the ice cools, it contracts, it snaps shut again, refreezing in subtle layers. This cyclical process may create the moon's astonishingly smooth surface younger than 60 million years, constantly renewed by tidal energy. On Earth, continents shift over millions of years. On Europa, the ice shifts every orbital sweep. It is one of the youngest, most dynamic crusts in the solar system, and all of it is driven by the rhythmic pressure of tides, the global clock that never stops. Tidal heating is not a one-time event. It is not episodic. It is not seasonal. It is continuous, enduring, as steady as the march of its orbit. Europa cannot escape this dance. It cannot stop flexing without breaking its orbital resonance with Io and Ganymede. It cannot slow the tides without altering the architecture of the Jovian system. Europa exists in an eternal balance. Too much tidal heating, the ice would melt entirely. Too little, the ocean would freeze solid. Just enough, a liquid ocean persists beneath a shield of protective ice. It is a planetary sweet spot created not by sunlight, but by gravitational choreography. Europa's inner pulse. When we look at Europa from space, its beauty seems delicate, almost fragile. But beneath that smooth white shell beats one of the most powerful internal engines of any moon in the solar system. A world warmed not by fire, but by motion. A world shaped not by volcanoes, but by tides. A world lit not by sunlight, but by the invisible pull of a giant planet. And this rhythmic energy, this hidden pulse, is what makes Europa a world of constant change, constant renewal, and possibly constant biological potential. Chapter 10: The Future of Europa. What happens when we finally touch the ocean? Among all the worlds orbiting our Sun, Europa stands apart as one of the most scientifically compelling. It is ancient yet active, frozen yet alive with motion, silent yet resonant with the possibility of an ocean deeper than Earth's Pacific, warmer than its poles, and older than its continents. In this final chapter, we look not at the past of Europa, nor the physics that define it, but at its future, a future in which humanity might, for the first time, directly touch an alien ocean, and perhaps discover that we were never truly alone. But before that future arrives, Europa demands patience, precision, and an understanding of the profound engineering challenges that lie ahead. 1. The challenge of reaching the surface. Europa is not an easy destination. It orbits Jupiter, a world so massive that its magnetic field traps deadly radiation thousands of times more intense than Earth's Van Allen belts. Any spacecraft operating near Europa will face an invisible storm of high-energy particles capable of degrading electronics within days. To study Europa's surface, a spacecraft must survive 5,000 millisieverts of radiation per day, temperatures near 160 degrees Celsius, surface pressures close to vacuum, constant gravitational tug from Jupiter, creating extreme orbital mechanics. This means our probes must behave like deep-sea submersibles wrapped inside interplanetary armor. Even the simple act of landing is an engineering puzzle. Unlike Mars, Europa has no atmosphere to break a descent. There is no parachute deployment, no aerobraking. A lander must rely entirely on propulsion, a controlled free fall onto ice that might be smooth like glass or jagged like shattered tectonic plates. The surface itself is unpredictable, chaotic terrain, sharp ridges, double ridge lines, and patches of ice that look as if they have been churned like the crust of a frozen ocean in slow motion. To reach Europa is difficult. To land on it is harder. To explore it, that is something humanity has never attempted before. 2. The first step, Europa Clipper and its mission. Launching in the mid-2022, NASA's Europa Clipper is the first major step toward unlocking Europa's secrets, but it is not a lander. Its mission is reconnaissance, a detailed mapping of everything Europa is trying to hide. Europa Clipper will carry a suite of advanced instruments: ice-penetrating radar to measure the thickness of the crust, thermal images to locate warm regions where the ocean may be closest to the surface, magnetometers to study the conductivity of the subsurface ocean, spectrometers to analyze the chemistry of surface materials, high-resolution cameras capable of capturing cracks and ridges only meters wide, plume detectors in case Europa ejects ocean material into space similar to Enceladus. Because Clipper cannot withstand Europa's radiation long-term, it will perform a series of quick flybys, dipping close to the Moon before retreating to safer orbits. Its job is simple: choose the landing site for a future mission. Where is the ice thinnest? Where are potential plumes located? Where are the chemical signatures most promising? Where is the ocean closest to the surface? In many ways, Clipper is the scout, the explorer surveying alien terrain, so future missions can strike with precision. 3. The Europa Lander, humanity's first touch. A Europa lander is the next logical step, an idea already in advanced planning phases at NASA. It will be one of the most ambitious robotic missions in history. Its primary goal is direct sample acquisition. Dig 10-20 centimeters into the ice. Extract material protected from radiation. Analyze chemistry on site. Even at these shallow depths, researchers hope to find salts from the subsurface ocean, organic molecules, amino acids, traces of potential biological processes, chemical disequilibria, signatures of energy gradients needed for life. The lander must work fast. Its lifetime could be only 20-30 days before Jupiter's radiation overwhelms its systems. Every hour counts, every sample matters, every measurement is a clue. If the lander detects even a hint of chemical activity associated with life, methane disequilibrium, amino acid asymmetry, or complex organic molecules, the implications would be enormous. Humanity would know where to drill, and the final phase would begin. 4. A cryobot, drilling through the ice. To reach Europa's hidden ocean, scientists propose a cryobot, a nuclear-heated probe designed to melt through kilometers of ice. The concept is both elegant and terrifying. A cylindrical robot is lowered onto Europa's surface. Its tip is heated using a compact nuclear source. The robot melts its way downward, sealing the ice behind it. A tether thousands of meters long transmits power and data back to the lander. Once the robot reaches the ocean, it deploys a hydrobot, a tiny submarine designed to explore the water below. This would be humanity's first direct contact with an extraterrestrial ocean. But several challenges remain. The ice may not be uniform. Embedded salt layers could refreeze around the cryobot. Pressure changes may warp the tunnel. Unknown microbes, if they exist, must be protected from contamination. Communication through the ice may degrade. And yet, the reward is beyond measure. 5. What we expect to find in Europa's ocean. Europa's ocean is not a passive reservoir. It is dynamic, energetic, and potentially habitable. Several scientific models predict hydrothermal vent systems at the seafloor, tidal heating generating persistent convection, mineral-rich vents similar to Earth's black smokers, organic molecules forming spontaneously, energy gradients suitable for chemosynthesis, a stable liquid ocean for billions of years. On Earth, life thrives in similar environments, without sunlight, without photosynthesis, powered only by chemistry. If life could evolve independently on Europa, it would likely begin here, in the warm fissures at the bottom of its global sea. Microbial life is the most probable, but scientists do not exclude larger possibilities. Tube worm analogues, simple multicellular organisms, gelatinous plankton, slow-moving filter feeders, chemical grazers drifting through the darkness. Europa might not be a quiet ocean. It might be an ocean full of motion. 6. The ethical question. What if we find life? Europa raises a profound question in planetary ethics. If Europa has life, do we have the right to disturb it? All robotic missions must follow strict planetary protection rules. Sterilization, anti-contamination, controlled descent, limited habitat disturbance. Europa's ocean could be a pristine environment unchanged for billions of years, perhaps the only biosphere besides Earth in the solar system. A careless probe could introduce Earth microbes into an untouched alien ecosystem. Thus, before we plunge a cryobot into Europa's ocean, humanity must decide: is discovery worth the risk? Do we observe from afar, or do we seize the chance to answer humanity's oldest question? 7. The moment of first contact. If a hydrobot ever reaches Europa's ocean, it will emerge into darkness. a darkness that has existed since the birth of the solar system, a darkness unbroken by sunlight, a darkness filled with possibility. In that moment, the probe's lights will flicker on, its sensors will open, its cameras will adjust, and humanity will stand on the edge of a world no one has seen. Will it capture drifting minerals, or shimmering organic particles, or a single microbe swimming across its lens? Or will it capture nothing at all, forcing us to confront the silence of an ocean untouched by biology? Either outcome holds immense scientific meaning, but one possibility would rewrite our place in the universe. 8. Europa's future is our future. Europa is not only a destination for science, it is a destination for philosophy. It invites us to confront the nature of life, the rarity of biology, the importance of cosmic environments, the relationship between oceans and habitability, and it challenges us to build technologies capable of touching another world's deepest secrets. Earth's oceans gave rise to life. Europa's may be doing the same, or may have done so long before Earth's first cell. 9. A silent world waiting for us. As we conclude this documentary, one truth becomes clear. Europa is not quiet. It is not still. It is not empty. It is a world in motion, shaped by tides, heated by friction, sealed beneath ice, and illuminated by the faint glow of Jupiter's reflected light. It waits. It holds its ocean like a secret, and someday soon, humanity will listen. 10. The story continues. Europa's story does not end here, not with flybys, not with landers, not with cryobots. Its story will continue as long as humanity has the courage to explore, to reach beyond the familiar, to touch the unknown, and to illuminate the dark ocean beneath a distant sheet of ice. The silent world of Europa is calling, and one day we will answer.